Hello everyone, welcome to the Luminous Science. Today we are going to see about an interesting topic and very important topic which is asked frequently in many of the competitive exams like UGC-NET, CSIR, GATE and many other state and national levels competitive exam, that is molecular spectroscopy. In this video, we'll see the important terms which are involved in molecular spectroscopy and also the type of electromagnetic radiations, their applications, especially which are related to molecular spectroscopy, and also regarding the vibrational spectra and infrared spectroscopy along with the energy level diagram of simple harmonic motion and also determination of force constant. So now let us see the definition. What does molecular spectroscopy mean? A molecular spectroscopy may be defined as a study of the interaction of electromagnetic waves and matter. So here simply spectroscopy or molecular spectroscopy can be easily defined, or the study which involves interaction between a electromagnetic wave and a matter. Or it can also be stated as molecular spectroscopy deals with the transition that a molecule undergoes between its energy level upon an absorption of suitable radiations determined by the quantum mechanical selection rule. Or we know that usually the electrons in an atom or molecule will excite from their ground state to excited state when they absorb the radiations which is equal to their frequencies, which is called as threshold frequency. So once such transition is seen between the energy level, and they are determined by the quantum mechanical selection rule. This is what molecular spectroscopy means. Now let us see, when it comes to molecular spectroscopy, there are two things we need to keep in our mind. That is, one is matter and the other one is electromagnetic waves. The electromagnetic waves, which are also referred to as electromagnetic radiations. Now we'll see what is this electromagnetic radiation. These are the form of energy which propagate through space at a constant velocity of light. So electromagnetic radiations are nothing but they are also a form of energy which propagate, which is nothing but moving through a space at a constant velocity of light. So at which speed these radiations will travel, which is equal to the velocity of light in vacuum, that is 3 into 10 to the power of 8 meter per second. And here in electromagnetic radiation, both electric field and magnetic field oscillate at a right angle and perpendicular to the direction of propagation. So when it comes to electromagnetic radiation, the two other important fields which we need to consider are electric field and magnetic field. So both electric field and magnetic field will oscillate at the right angle, which is nothing but perpendicular to the direction of propagation. Now, if we consider a graph here representing both electric field and magnetic field, the waves are represented as follows of both electric field and magnetic field. And we can see here both the field, that is electric field and magnetic field, are perpendicular to each other, which is nothing but they're right angled, that is 90° to each other. If we represent them through axis, we can see this is the z axis and perpendicular to this is y axis, and perpendicular to y we can see the x axis. So this is the direction of the wave that travels of both electric field and magnetic field. Here E, that is electric field, is oscillating in XYZ plane because interaction of electromagnetic radiation, its matter is more commonly through the electric field. So usually in electromagnetic radiation comprehending spectroscopy or spectroscopic studies will majorly consider the electric field rather than the magnetic field. The magnetic field is also used in other different types of spectroscopy, which we'll be studying further. Now let us see some of the important terms which are involved in molecular spectroscopy or also usually in spectroscopy. The first one is wavelength, which is represented by the term lambda. So what does wavelength mean? The constructive distance between any two crest or trough is called as wavelength, and it is represented in the units of Armstrong, nanometer, micrometer or meter also. Now if we see what is this wavelength, refers to the consecutive or the constructive distance between any two crest and trough, which is nothing but the distance between here to here or here to here. So the distance between these crest and trough is called as wavelength, which is represented in terms of Armstrong, nanometer, micrometer or meter. Now let us see what does frequency mean. Frequency, which is represented by nu. The number of waves passing through one point in 1 second is called as frequency. Frequency, which is nothing but the number of waves passing through one point in 1 second, is called as frequency, which is represented or expressed in terms of per second or hertz. Hertz, which is also written as Hz. So to explain frequency, if we consider this as one of the point, one wave is nothing but starting from here to here. So this will consider one wave. So From this point, how many such waves are passed in 1 second is referred to as frequency. That is what here given, the number of waves passing through one point. That is one point in 1 second. In 1 second, how many such waves will pass from this point, that is from one particular point, is called as frequency, which is expressed in terms of per second or hertz. And the next term we are seeing is amplitude, which is represented as capital A. This is nothing but the height of crust or height of trough is called as amplitude. So if we see this as a wave, so the height of a crust or a trough, the height, this is called as amplitude. And the fundamental equation of electromagnetic radiation, we know that there is a fundamental equation for electromagnetic radiation, which is E is equal to h nu, or and nu lambda is equal to C. So these two equations are very important, which you need to remember to solve many problems. Some problems will be given directly and you need to use simple equations like this. The questions may be asked for 2 marks and or else also for sometimes 3 marks. Such simple questions will be asked, for which you need to remember these equations. The first one is E is equal to h nu and h lambda is equal to C. Here we can see E is nothing but energy of radiation, h is Planck's constant, nu is frequency of the radiation, C is velocity of light, and lambda is wavelength of the radiation. Now let us see the regions of spectrum. So spectrum, which is also known as spectroscopy, here there are mainly 8 types of spectrum or radiations, which is very important. Now if we see into the spectrum, there are mainly 8 important spectrum, and using all these 8 types of different spectrum, we can study different characteristics of different molecules. So from NMR and ESR, we can study the change in spin of an electron within an atom, and from microwave we can study the change in orientation of an electron, and in IR spectroscopy, that is infrared spectroscopy, we can study the change in configuration. And using UV visible spectroscopy along with X-ray and gamma ray, we can study the change in electron distribution. So all these studies and in depth and detail we'll study in our further videos. Now we'll just concentrate only upon the types of electromagnetic radiation and the molecular spectroscopy. Now let's see the different types of spectrum and their characteristic, at what range to what range they actually lie in. So here are the characteristics that we are going to discuss, that is wave number, which is expressed in per centimeter, wavelength, which is expressed in centimeter, frequency expressed in 3 into 10 to the power of 6 hertz, and energy, which is expressed in joule per mole. So now we'll consider 6 spectrum, that is NMR, ESR, microwave, infrared, and visible. So their wave number actually lies from 10 to the power of 2. And here it is 1, here 100, 10 to the power of 4. So all these wave numbers are expressed in terms of centimeter inverse. Similarly, when it comes to the wavelength up to which they can range, which is expressed in terms of centimeter, for NMR and ESR it lies around the range of 100, and ESR microwave it is 1. For microwave and IR it is 100 micrometer, and for visible it is 1 micrometer. And when we see about the frequency range, for NMR and ESR it lies in 3 into 10 to the power of 8, and for ESR and microwave the mid region or the range lies in 3 into 10 to the power of 10. For IR it is 3 into 10 to the power of 12, and for the region between the IR and visible it is 3 into 10 to the power of 4. And the energy, which is expressed in joule per mole, when the molecule lies between the range of NMR and ESR is 10 to raised to the power of -1. For ESR and microwave it is 10. Between microwave and IR it is 3 into 10 to the 10 raised to the power 3, and for IR and visible it is 10 raised to the power of 5. Now if we see the X-ray and gamma ray, that is, this is the wave number expressed in centimeter inverse of 10 power 6 and 10 power 8. Their wavelength expressed in centimeters, that is 10 nanometer and 100 picometer. Their frequency range is 3 into 10 to the power of 16 and 3 into 10 to the power of 18 respectively. Their energy, which is expressed in joule per mole, is 10 power 7 and 10 power 9 respectively. Now let us see a brief definition about the different spectrum. The first one is radio frequency region. The radio frequency is used in NMR and ESR. So here energy change involved in that form the reversal of spin of the nucleus or electron. So using radio frequency in NMR and ESR, we will see the reversal of spin of electron, which is involved in the transition. And in microwave region, which is used in rotational spectroscopy, here spectrum between the rotational levels of molecules are measured. And when it comes to infrared region, which is used in vibrational spectroscopy, here the main important point is the separation between the levels, that is energy level is 10 raised to the power of 4 joule per mole. And when it comes to visible and UV region, we'll use electronic spectroscopy. Here, usually the transition of electron between the energy levels will be seen. And when it comes to X-ray region, energy changes involve the inner electron of an atom or a molecule. So here, usually in an atom, we consider the inner core electrons which is involved in the transition. And when it comes to gamma ray, the energy change involve the rearrangement of nuclear particle. Nuclear particle, which is nothing but neutrons and protons. So usually in gamma region, we'll see the change in energy by the rearrangement of nuclear particles, which is nothing but protons and neutrons. Now let us discuss about the molecular energy level. The internal energy level of a molecule may be considered as a sum of electronic, vibrational, rotational and translational energy, that is given by E internal. That is, the internal energy is nothing but the sum of electronic energy, vibrational energy, rotational energy and translational energy. Since translational energy is not quantized, so it is negligibly small. We know that translational energy will always be smaller when compared to the other three energy, that is of electronic, vibrational and rotational. Thus, the translational energy will be neglected and therefore the internal energy of a molecule will be equal to the sum of electronic energy, vibrational energy and rotational energy. Now let us see what does rotational energy level mean. It involves the rotation of molecule about the center of gravity or a part of a molecule, which is nothing but if we consider a gravitational force which is passing through a molecule perpendicular to the molecule, the rotation of a molecule which is involved with respect to the center of a gravity will be measured. Like for example, if we consider a molecule and the gravity is acting in this direction, that is which is perpendicular to the direction of its rotation, and molecule is rotating anti-clockwise, if we consider, so the rotation at what speed the rotation is occurring and what are the changes the atomic particles are undergoing due to this rotation is nothing but rotational energy level. The energy level also, and due to this rotation the electrons will also get transisted or excited or may also return from their excited state to ground state. All these are studied using the rotational energy level. Now, when it comes to vibrational energy level, it is associated with stretching, contracting or bending of covalent bond in a molecule. So, the vibration, this is usually involved or this is associated with the stretching, which is nothing but expanding of a bond, or contracting or compressing of a bond or bending of a covalent bond. So, vibrational energy level will involve these three important movement, that is stretching, contracting or bending of a covalent bond in a molecule. So, in vibrational energy level, we'll consider covalent bonds. And thus, due to the vibrational energy level, which is caused due to the stretching, contracting or bending of a covalent bond in a molecule, the bond behave as a spiral mode of wire. We know the spiral rings which are present. So, the bond in between the molecule will behave as a spiral. As it involves the stretching, contracting and bending, it behaves as a spiral mode of wire. Now, let us see what is electronic energy mean. It involves change in the distribution of electrons by splitting of bond or the promotion of electrons into the higher energy level. As mentioned in the definition only, the electronic energy level is associated with the distribution of electrons in each energy level, and also promotion, which is also called as transition of electrons from their ground state to higher energy state or excited state. Now let us see the concept of absorption and emission spectra. Now we'll consider two molecular energy level, En and Em. So here we can see the absorption. So here if we consider a molecule or an electron present in the ground state, when the radiation passes through the ground state of an atom or a molecule, the electron will absorb this radiation and will get excited into the state of Em. So here we can see the excitation of electron from the ground state En to the excited state Em. And this phenomenon is called as absorption. And if we come into the case of emission, after some time or also after few seconds, the excited electron will return to its ground state, that is from Em to En. So during the course of getting back to its ground state, this electron will emit some amount of radiation which might be or may not be equal to this incident radiation. And the process by which it will emit the radiation when it depromotes from excited state to ground state is called as emission. So this is the explanation for absorption and the process of emission. Now we'll see an explanation related to this. If a photon of frequency mu falls on a molecule in the ground state and its energy h nu is equal to the energy difference between the two molecular energy level, then the molecule undergoes a transition from lower energy level to the higher energy level with the absorption of a photon of energy h nu. The spectrum thus obtained is called as absorption spectrum. So here we can see, here if we consider an electron and there is a radiation which is incident to this electron. If the frequency of this incident radiation is equal to the energy distance between these two, that is here mentioned delta E is equal to Em minus En. So the energy or the frequency of the incident radiation should be equal to the energy difference between these two energy level. Then only this electron will absorb one of the photon and will get excited to the excited state from its ground state. And the spectrum which is obtained from this transition is called as absorption spectrum. And similarly, if a molecule falls from the excited state to the ground state with the emission of a photon of energy h nu, the spectrum obtained is called as emission spectrum. Here, as said earlier, if the electron from its higher energy level or excited state will get depromote and falls back into its ground state En by giving out a photon with a frequency h nu, and the spectrum which is obtained by this is called as emission spectrum. Now let us see the selection rule. So before going into a detailed understanding of a selection rule for rotational spectrum, now let us see what is actually a selection rule and why selection rule is more important. So selection rule is a condition that specifies or determines whether a transition between the two energy level is allowed or forbidden when an atom or molecule absorbs or emits a electromagnetic radiation, which is nothing but when an electron will absorb a radiation, which is nothing but electromagnetic radiation. So the electron might absorb or may release some amount of electromagnetic radiation with their respective frequency. When that happens, the flow of electron or the movement of electron from its higher energy level to lower energy level or from lower energy level to higher energy level, are these transition allowed or not is governed by the selection rule. So the detailed explanation of selection rule, how the selection rule were made, what are its purpose, how do we judge the transition based on selection rule will be covered in the next session. Now we'll see what are the importance of selection rule, and we got to know that selection rule is needed to know the forbiddenness or the permission or not permission, the forbiddenness or the allowed transition of an electron between their energy level. Now let us see what are its important. By knowing the selection rule, we can predict which transition can occur and explain the appearance of spectral lines, and which also helps in the interpretation of atomic and molecular spectra. Now let us see the selection rule for rotational spectrum. Atomic spectrum as well as molecular spectrum are obtained due to the transition which takes place between the energy level. But however, such transition can occur only between a definite energy level and not just between the any two energy levels. So the electron transition should occur between the definite or a discrete energy level, not to any one of the energy level. Like for example, if we consider there are 4 energy levels, and the electron from 1 should only jump to 2. This is only valid. The jump of electron from 1 to 3 is also not allowed, and 1 to 4 is also not allowed. In the same way, the depromotion of electrons from 4 to 2 is not allowed, but the depromotion of electrons from 4 to 3 is allowed. So this is what the selection rule of atomic spectrum first point says. And so the restrictions thus applied on the transitions are governed by certain rules which are called as the selection rule. Now let us see what are selection rule, what are the points involved, and for what transitions are these applicable. Let us see the first point. If the selection rule are followed, the transition can occur and it is called as allowed transition. If the transition are allowed, then the term we define is called as allowed transition. Then if a selection rules are not followed, there are certain selections rule which need to be followed. If the transitions cannot take place, and it is called as forbidden transition, or if in case if any transition does not obey the selection rule, they are called as forbidden transitions. And the selection rule are generally expressed in terms of changes in quantum number for allowed transition. Like for example, for a pure rotational transition, the selection rule which is given by delta J is equal to plus or minus 1. Here J represents the rotational quantum number. So delta J, which is equal to plus or minus 1, corresponds to absorption and minus 1 corresponds to the emission. So from this example, we got to know that the transitions are only allowed or followed when the electrons jump from their energy level to their consecutive energy levels. It might be excitation or depromotion of electrons from their higher energy level to lower energy level. And similarly, for a And similarly, for a pure vibrational transition, the selection rule is delta V is equal to plus or minus 1, where V represents the vibrational quantum number. And similar to the rotational transition also, in vibrational transition also, the jump of electrons or transfer of electrons from one energy level to another energy level is only to their consecutive next energy levels. The selection rule describes how the probability of transition from one energy level to another energy level cannot be zero. That is, since every energy level has their own discrete energies, the transfer or movement of electron from any energy level to their consecutive next energy level cannot be zero. And thus, it has two sub-pieces, that is, gross selection rule and specific selection rule. If we see the definitions, a gross selection rule illustrates characteristics requirement for atoms or molecule to display a spectrum of a given kind, such as an IR spectroscopy or a microwave spectroscopy. Once the atom or molecule follow the gross selection rule, the specific selection rule must be applied to the atom or molecule to determine whether a certain transitions in quantum number may happen or not. So gross, as the name itself suggests, gross is nothing but the overall or the total movement of electrons from their lower energy level to higher energy level. So the overall gross selection rule will be characterized, and we'll get to know that the spectrum obtained due to the transitions are the transitions which causes the spectrum are followed or forbidden. Now let us see the conditions to obtain a pure rotational spectrum. So to obtain a pure rotational spectrum, as we know, the selection rule should be followed. That is, delta J is equal to plus or minus 1. And apart from that, the molecule must have a permanent dipole moment so that it can interact with the electromagnetic radiation and absorb or emit a photon. So apart from following the selection rule, that is delta J is equal to plus or minus 1, the molecule which is under the study for its pure rotational spectrum should have a permanent dipole moment. Now what is this dipole moment? Dipole, as the name itself suggests, pole, which is nothing but north pole and south pole, which we can also say as negative and positive poles or charges. Di, which is nothing but both. So a molecule will contain both positive and a negative charge. So to know the exact definitions of dipole moment, let's see its definition. A dipole moment is the measure of separation of positive and negative charge in a molecule, and it indicates the polarity of the bond or a molecule. And dipole moment is expressed in terms of Coulomb meter or dBi. So in simple words, we can also know the measure of separation. If there is a positive charge and the negative charge, the measure at the separation, at what energy they can be separated or at what distance are this positive and negative energy are separated is measured, and that is known as dipole moment, which is most important to get a pure rotational spectrum. And so to get a pure rotational spectrum, the molecule given should by only have a polar molecule. That the molecule which is under the study, or to obtain a rotational spectrum, we should have a polar molecule. And consequently, homonuclear diatomic molecules like H2, N2, etc. and symmetrical linear molecules like carbon dioxide, methane, ethane do not give the rotational spectrum. So they do not give rotational spectrum because they are linear and symmetric, and therefore if they undergo a vibration also, there will be symmetric linear molecule. Due to symmetric, there will be no changes in their rotation or also vibration, which will not give us a proper spectrum we are looking for. And thus polar molecules like HCl, CH5Cl, carbon monoxide, water, nitrogen oxide, dinitrogen oxide, etc. will give us the pure rotational spectra. Now let us see the rotational spectra of diatomic molecule. So now we'll consider a diatomic molecule in which M1 and M2 are the masses of two atoms and R is the bond length rotating about an axis passing through its center of gravity. So for this we'll consider two atoms which is with the masses M1 and M2 which are separated by a distance of R, and here C represents to the center of gravity which is acting exactly at the center of the distance between the M1 and M2. Here R1 represents the distance between the center of gravity and to the center of the atom A of mass M1, and R2 represents to the distance between the center of the atom B of M2 to the center of gravity C. So we'll see here masses M1 and M2 are joined by a rigid bar which is the bond length. So they are joined by a rigid bar which is its bond length, whose length is given by R, which is bond length, which is equal to R1 plus R2. Here it is R1 plus R2. We'll consider this as equation number 1. The molecule rotates end over end about the point C. So the molecules are rotating with respect to the center of the gravity, that is in end-to-end motion, that is both are in the same direction. The center of gravity is defined by the moment about it. So the center of gravity is defined in what direction or in what movement are these molecules are involved in. that is which is given by m1 r1 which is equal to m2 r2. Let us consider this as equation number 2. Now, if we consider the moment of inertia about C, so as we know, moment of inertia is represented by I, and moment of inertia is the measure of bodies resistant to rotational motion about a given axis. That is, up to what extent the rotation can be restricted about the center of an axis of a molecule which is under the study of rotational spectrum. And it also depends on mass of the body and how the mass is distributed relative to the axis of rotation. So the moment of inertia, it is mainly dependent upon the mass of the body which is involved in the rotational motion, and also in what direction the movement of rotation is taking place, along with the distance between the two mass bodies involved in the rotation. And from the definition of moment of inertia, we got to know I, which is equal to summation of I to I. So here we are considering the rotation, multiple rotation, thus summation I to I with I to I into mi into ri square. Let us consider this as equation number 3, where r is the ith particle, distance of ith particle of mass mi from the center of gravity. And since the diatomic molecule has 2 atoms, we have I is equal to diatomic molecule, which is nothing but 2 atoms, which forms a molecule. So we can write as I is equal to m1 r1 square plus m2 r2 square, which is as equation number 4. And from equation number 2, that is m1 r1 is equal to m2 r2, we can write equation number 4 as I is equal to m2 r2 r1 plus m1 r1 r2. And upon simplification, we'll get I is equal to R1 R2 into M1 plus M2. We'll take R1 R2 as common, and remaining M1 plus M2 will be written as it is, which we'll consider as equation number 5. And however, from equation number 1 and 2, we know that M1 R1 is equal to M2 R2. So which is equal to M2 into R2 minus R1, which will be equation number 6. And therefore R1, which is equal to M2R divided by M1 plus M2, which is equation number 7. And similarly R2 will be equal to M1R whole divided by M1 plus M2, which will be equation number 8 respectively. And substituting the values of R1 and R2 from 7 and 8 in equation number 4, we'll have I is equal to M1 M2 square whole divided by M1 plus M2 whole square into R2 plus M1 square M2 whole divided by M1 M2 whole square into R square, which on simplification and taking LCM, we'll get I is equal to M1 M2 of M1 plus M2 into R square whole divided by M1 plus M2 whole square. So in the next step, the square and this part will get cancelled, and we'll remain with M1 M2 whole divided by M1 plus M2 into R square. So this is nothing but the reduced mass, which is expressed in terms of nu, which is given by M1 M2 whole divided by M1 plus M2. And therefore we'll get our final equation, that is I is equal to nu into R square, which is equation number 9, where mu will be the reduced mass, which is expressed as mu is equal to M1 M2 by M1 plus M2, and I is moment of inertia and R is the internuclear distance. So this is the final equation to obtain the moment of inertia and also to express the pure rotational spectrum of diatomic molecule. Now let us see the expression for rotational energy. So if they ask you to express the rotational energy of diatomic molecule, then you need to start the equation from considering the masses and also continue till here. And if they ask you only to express the rotational energy of diatomic molecule only in terms of moment of inertia, then you will need to stop till here. But if they ask you to express for rotational energy, then you need to continue till the end expression. And we know that generally the angular momentum, that is L of a rotating molecule, is given by L is equal to I omega, which is equation number 10, where this omega will be the angular velocity. And however, the angular momentum is quantized. The value is given by, this is the general expression we need to memorize, that is L is equal to square root of j plus 1 into h by 2 pi. We'll consider this as equation number 11, where j will be equal to 0, 1, 2, 3, etc. And h is the Planck's constant, and pi, we know it is a constant value, that is 3.14. Now, since we got to know that j is equal to 0, 1, 2, 3 and it goes on continuing, these are called as rotational quantum numbers. And further, the energy of a rotating molecule, E, is given by 1 by 2 I omega square. Now multiplying and dividing this, E is equal to 1 by 2 I omega square by 2I, we'll get the following equation, that is E is equal to I omega square by 2I. And we know that I omega square, which is nothing but L. So we'll, considering the equation number 10 and substituting this, we'll get E is equal to L square by 2I, which is equation number 12, where L is the angular momentum, I is moment of inertia. And using the expression for L, we have E, which is equal to j of j plus 1 h square by 4 pi multiplied by 1 by I 2. And upon simplifying this, we'll get E is equal to j of j plus 1 h square by 8 pi square I. And here we know that j can be 0, 1, 2, which continues, which is expressed in terms of joule. But we usually express in terms of centimeter inverse. This is done by dividing the energy in joule by Hc. So dividing this term by Hc, one of the H will get cancelled and we'll end up with the equation E is equal to H by 2 pi square Ic j of j plus 1, which is expressed in terms of centimeter inverse. And to still simplify the expression, we write E is equal to Bj of j plus 1, where B is equal to H by 8 pi square Ic, where B is the rotational constant. And to understand this, we'll take up an example and solve. That is, we'll consider a HCl molecule. So if J is equal to 0, E will be 0. If J is equal to 1, then we'll get the energy as 2B. If J is equal to 2, 3, 4 and so on, the energy will also be 6B, 12B, 20B, etc. Now, if we consider the rotational energy level diagram for a diatomic rigid rotator, we'll consider this energy level diagram with the J value and also with the energy. Now, if J is equal to 0, then energy will be 0. If J is 1, energy will be 2B. If J is 2, 3, 4, 5. Similarly, the energy value will be 6B, 12B, 20B, 30B respectively, which can be expressed as it is. Now, we'll see the calculation of bond length. By determining the frequency spectrum, that is delta nu bar, it is possible to calculate the moment of inertia I of a molecule using the equation B is equal to H by 8 pi square Ic. And then by knowing the masses of the atoms present in a diatomic molecule, it is possible to calculate the distance between the atoms R with the help of the equation I is equal to m1 m2 by m1 plus m2 into R square, which we can also write as mu R square, as mu is the reduced mass. So the bond length can be calculated using these two formulas. Depending upon the data they have given or the data we know, we can use those given data and substitute them to the corresponding any of the one formula to obtain the required data or the value we are searching for. Now let us see what are the applications of microwave spectra. Microwave spectrum, it is used to determine the bond length of diatomic and polyatomic molecule. They are useful in the study of internal rotation and inversion of spectrum of ammonia. And microwave radiation, it is used as a cooking device in kitchen, that is microwave oven. These were about the informations of molecular spectroscopy, which is very important in many of competitive exams as mentioned earlier, and also in your semester examinations. We'll see in the next session how the vibrational spectra and infrared spectroscopy and involved, and along with energy level of simple harmonic oscillation in the part 2 video of molecular spectroscopy. Hope you have liked this video. If you have liked this video, kindly subscribe to the Luminous Science. See you all in my next video. Thank you.